phase diagrams. So phase diagram is like a map that shows us what state a substance is in, or phase it is in different pressure and temperature areas. So we graph pressure on the y-axis, temperature on the x-axis, and I'll just give you a peek here. So this is a phase diagram for water. So pressure here, and this is not to scale, temperature not to scale. And so we see this is regular atmospheric pressure, right? So at a temperature of 0 degrees, that's where you have a transition from solid water to liquid water. If you are below 0 degrees Celsius at 1 atmosphere of pressure, then the ice is a solid. If you are in the temperature range between 0 and 100 degrees, the water will be a liquid. And if you're above 100 degrees, the water will be a vapor. And so we can read at one pressure, we can just go straight across and see what's happening. There's a place, though, where the solid, the liquid, and the gas intersect, and that's called the triple point. And at that particular pressure and temperature, all the three states are present at the same time. Up here we have the critical point. Temperature above this, there's no more line because there's no more distinction between liquid and gas. It's a supercritical fluid. But here we have all three states present. The regions in that diagram represent conditions where that particular state is stable. The lines or the curves represent the set of temperatures and pressures where you have an equilibrium between those two states. So there's a vaporization curve, a sublimation curve, a fusion curve. So let's just identify those. Now this is the sublimation curve. So if you want to know, well, at what temperature will ice sublime? Well, at certain pressures, this will tell you. And the vaporization curve, the fusion curve. So one of the funny things about ice is if you increase the pressure on the ice, the melting point goes down. This curve slants to the left. That's not typical. But that's why ice skates work. Because when you put your weight on that thin blade of the ice skate, it puts a lot of pressure on the ice and causes the surface layer of the ice to melt, which makes it much slipperier. And so you're able to glide around on the ice. And that's an unusual thing. Most substances have a positive slope on their fusion curve, and so if you increase the pressure, the melting point goes higher. So let's watch this video about the triple point. This is not water. So they're pulling a vacuum on this flask, and so they've got this liquid to boil. And now the pressure continues to go down. So you see that over here? The liquid's beginning to freeze. So you have solid, and now it's boiling too. So you have solid, and you have liquid, and it's boiling. Is that trippy or what? A freezing liquid boiling.
So water, when you put water in an ice tray and you freeze it, it's at some point it's going to do that?
No.
No. Oh, okay.
No. This is not happening, and this isn't water.
Yeah.
It's not happening at atmospheric pressure.
Oh, okay.
They've reduced the pressure. They've attached a vacuum pump, and they're pulling a vacuum on it, so they're reducing the pressure. And now it's frozen solid.
And by reducing the pressure, you're increasing the freezing temperature. Right?
Well, let's look at the heating. Let's look at something that's maybe a little more normal. So these are two other substances. Let's just look at this. This is iodine. So the triple point is right here. So this substance, you could get the triple point to happen at 0.118 atmospheres. So you're decreasing the pressure, and this will happen at 114 degrees Celsius. The triple point for carbon dioxide is at 5 atmospheres and minus 56.7. So if we go back, I think this is water. The triple point for water would happen right here. That's at 0.01 degrees Celsius and 0.006 atmospheres. So a very, very low vacuum. And then you can have freezing boiling water. But this diagram illustrates how you can navigate the phase diagram. And I kind of went over this already, but you can look at 1 atmosphere of pressure and say, well, if I start at minus 25 and I keep the pressure the same and I just increase the temperature, what happens? So this is a little bit like that heating curve. It's just a different representation. You've got a solid and you get to 0 degrees and it melts, and then you have a liquid until you get up to 100 degrees and then it boils and you have a gas. Or you can take a given temperature and see what happens when I change the pressure. So here I have 1 atmosphere of pressure, and if I pull a vacuum on the water, it's a liquid. And I get down here, this is not as low as the triple point, but still a pretty low pressure, and now the water will boil at room temperature. And this is one of, I don't remember a lot of things from high school, but I have some very, very clear, they're almost like movie clips, right? You have that? Of course, your high school wasn't that long ago. Anyway, so high school chemistry, Mr. Floyd Sturdivant was my teacher, crazy guy in a white lab coat. One day he had this big vacuum flask with water in it, and he hooked it up to a vacuum pump, and that started chugging away, and he was giving his lecture and stuff, and then the water started to boil. And there were no tricks. There was no hidden heating element under the bench top. It just started to boil. And then he made all of us come up and put our hand on the flask. And of course, the first person is a little scared, right? Would you put your hand on a flask of boiling water? Not unless you wanted to burn. But we all touched it, and it felt like touching the bench. It was room temperature, and the water was boiling, and our minds were just blown. Yeah.
So it's like a nitrogen gas?
Well, no, it's not like nitrogen gas. We just decrease the pressure until we get to this point where at 25 degrees Celsius, the liquid and the gas state are in equilibrium with each other.
When we worked on air conditioning systems, when you open it to atmosphere, you get just air, you get regular air in there, and the water can end up condensing and causing problems. So before we refilled it with Freon, we would have to run a vacuum on it to
You get all the air out.
The air. where the water, vaporize the water and suck all the water out.
Yeah. So refrigeration systems operate by expanding and condensing a gas. And when you condense the gas, the temperature changes. And when you allow it to expand, the temperature changes. Yes?
That question, like if we're living in the low pressure, with blood boiling.
Yeah, if you were trying to live at very low pressure, your blood could boil. Yeah.
So you don't die.
Yes, you would die. Aside from not being able to breathe. But yeah, like out in space, there's no air, right? What's the pressure out there? I don't know. It's probably pretty low. Could your blood boil out there? Yeah, probably could. Some of the things that you see in science fiction books and movies and stuff are not all that crazy, actually. They're just truth taken to an extreme. Okay, let's see where did I cover everything? Did that. I looked at this one. So each substance is going to have its own unique phase diagram. Here for iodine and for carbon dioxide, this fusion curve has a positive slope instead of a negative slope. Right? Water is not typical. Another weird thing about this one, carbon dioxide, there's no stable liquid state at 1 atmosphere. So here you have 1 atmosphere, and that hits the sublimation line. That's why it doesn't melt. In order to get liquid carbon dioxide, you have to get up above 5.1 atmospheres to get liquid carbon dioxide.
So like propane, when you fill a propane tank, it's liquid propane inside of the
Yeah, so you go buy LP gas for your grill, and it's a liquid because it's under high pressure. Because if you take a gas and you increase the pressure, you're going to liquefy it at some point, at whatever temperature. If it gets too cold, though, then you could end up freezing it. But for CO2, I mean, here we're talking about really, really cold temperatures down there. And the triple point for CO2, the critical point for CO2 happens at 31 degrees Celsius and 72.9 atmospheres. But you can get supercritical CO2 at a temperature that's actually not even as warm as body temperature. It just requires a great deal of pressure. Because you wouldn't want to wash coffee to get the caffeine out with a hot liquid, right? Because you could destroy some of the compounds in the coffee bean. But here at 31 degrees, you can get supercritical CO2.